Hello, Lisa, and everybody else who's joining. Hopefully, everybody's doing well. So, here for the Saturday stream, talking about some science and math. I'm going to focus on math today. Um, Throughout the week, I'm a bit thinking about what's the most exciting thing for the week to talk about. This week was actually a pretty difficult week, some complicated things that I'll probably get into in the future. Like in quantum 2, we're talking about perturbations of quantum states. So, in quantum 1, we talked about basically quantum states that are ideal, I guess you can say. Within technology, for instance, we perturb quantum states by, for instance, introducing electric fields, and there's a bit more. You have to calculate corrections for that. Thermodynamics is actually quite complex. It's been what 2 weeks so far. We're still on the first chapter, I guess, like the first half of the first chapter. So y'all probably remember that I read through chapter 2 before I had that talk uh, uh, with the globe denier, and with the depth that we're going into in each chapter, in each section. It's amazing. So I'm finishing up the homework. We've had 2 weeks to do the homework. I'm on the last few problems. So I'll probably talk about some of the thermodynamic stuff in the future after I figure it out a bit more. So it helps explain and let me know if my audio is going well. Did a different what do you call it, process. Oh, it's good, good, awesome. And is the video good as well? Awesome, thanks. Good, good. So as you can see, it looks a bit different. I hope to make it a bit more snazzy. Took a little while to get it set up, and it still does. But one of the things that I ran into both in my thermodynamics class and my relativity class, which I talked about a little bit, and I believe in my cosmology class as well, was differential equations, different differential equations, derivatives, and limits, which I've always hated limits. So all of those things that we learn about in class that just seems like courses, and they are just courses, but the stuff that you learn therein, you do need them later. So I figured it would be good to talk about some of these foundational things that become very important. Basically, it's like these are the sort of things that has to become second nature when you start getting into higher physics. Lisa says partial differential equations makes my brain explode. Yeah, they can be funny. Uh the simpler ones. At least if you don't keep up with it. The one that we did that we had to do for a problem is actually a pretty simple one, but I didn't remember exactly how to solve it. My professor helped me out in office hours. So the first thing we'll talk about are limits. So limits actually lead into derivatives, and then derivatives. We'll talk a little bit about differential equations, and I may bring in the Hubble constant a little bit for a little bit of a practical when I talk about my cosmology book a bit. So those are the things that we'll have in store for the next hour. Some limits, some derivatives, some differential equations, and maybe a little bit of cosmology. So to start with the limits, so limits are not necessarily limits as in like a limit on something, but it's basically getting close to the culmination of something. So for instance, the way that this book describes it, which I think is pretty cool. So if you look at figure 2 at the bottom on the left there, it talks about the two different kinds of lines. So if I have a curve here, we can say that I have a tangent to the curve, and the tangent will cross the curve at one point. So it's basically skimming across the curve, touching at one point, and that's a tangent. But a secant curve will cross at 2 points. So this curve here would be secant. So we can see that the secant curve, it crosses here and it crosses there. And the reason why this is important is because the secant curve allows us to sort of graphically describe what's going on with the limit. So basically, the limit would be, if I look at this vector, just drawing an arrow makes it a vector, and I also say, let's say that this is a particle or even a planet. We was talking about that last week, even a planet going in orbit. Well, if I was to take the velocity of the planet at this point, like we did with the analogy, we put a radar detector on the planet, what would be the velocity at that point? And that's the velocity we got last week, about what it was, about 30 kilometers a second. So that would basically be the instantaneous velocity at this tangent point where the tangent line crosses the uh, curve. But let's say we don't have all of those details. What we can do is we can simply take the secant line and we can make out of these two a slope and bring that slope closer and closer to into congruence with the tangent line, and then we could approximate or derive in a sense what the slope will be, at least what the tangent will be. So utilizing the example from the book, they utilize a parabola, which you might be familiar with, is just the y equals x squared. So this is the x plane, this is the y plane. Every x that we have, we square it, and the graph looks like this. Well, if I wanted to get the tangent line at this point, what I can simply do is, since I can't necessarily get a slope because that's just one point, let's say I call this point T, what I can do is I can actually draw a secant line and say I'll make myself a slope out of the 2 points in this secant line. So let's say that this is my point Q, to use the notation of the book. And let's say my point T is 1, 1. Well, the slope is rise over run, which means it's the direction that we're going in the y-axis over the direction that we're going in the uh, x-axis. So we can call that a difference. So we can say it'll be the change in y over the change in x, the difference between these 2 points. Now, Q, we don't necessarily know what it is. We just know that it's still in the same x squared graph. So what we can do is we can say that the curve is going in this direction, hitting P first. So we can say that the change will be x squared minus 1 over x minus 1. So this would be the P point, and the other numbers would be the Q point. And what we're doing is we're getting a slope between these two lines. And this would allow us to get a a point that we can graph or construct a line from that equates to this uh, uh, tangent line that gives us a slope at that point. Now, the way this can be written as in a limit form, it will be the limit, and because this uh, point here is 1, 1, because we decided that that's going to be our tangent point, it'll be the limit x goes to 1, since x is the variable that we're putting in to get y. The limit as x goes to 1 of x squared minus 1 over x minus 1. And the solution to that will be the slope of the line at that point, for which we can get our tangent line. So if there's any questions, let me know. And so why don't we try this out? So let's say that to utilize the books example, they usually has a few harder numbers, but I'll just use like I have a table here on the left side. You see this table on the left. So for instance, and some of these might be a bit mixed up from different problems, but the idea is pretty much the same. So let's say if I make my Q x is 2, so that means it'll be 4 for y. So if I was to just get the slope of that, it'll be 4 minus 1 over 2 minus 1. So that's going to be 3 over 1. So that's 3. So what that means is that between these 2 points at this secant line, we also draw a third line between these two. The slope between these two, given those 2 points, is 3. That's a slope there. And what the limit does is it just takes this line here with a slope 3 and it moves it a little bit closer and a little bit closer and a little bit closer. And the limit is going to be when this purple line overlays directly on top of the red. That's when we reach the limit of the convergence of these two lines and we get the actual slope or the actual change, ironically, in position or the velocity at that point. Now, the interesting thing, which always ticked me off about limits, is how unusual they are to do in some senses. So basically, what I did was I got this answer by plugging in the numbers of 2 points, right, from this equation here to get the slope. But now let's go ahead and actually solve this as a limit, right? So one general thing you can do if you want to get the limit of something, a good first choice to try is to simply plug in what the value is. So again, basically we have these 2 points. We're trying to get the limit between P and Q. Rather than just plugging in numbers at that point, we actually want the complete limit as if we rotate that secant directly to the tangent line. So we might say, let's say plug in 1, and 1 squared is 1 minus 1, and 1 minus 1, so that's 0 over 0. So of course that doesn't work. So the thing that happens is, which I used to always forget about when I was in the class, but ironically I remember now, but maybe that's the purpose of the class. What you have to do is try to simplify this thing as much as possible. So what we can do is, and when I say simplify, we need to put it into more less complex forms. Like this is if something is squared, we can see that. So if I was to take the factorization of this would be x plus 1, x minus 1 over x minus 1. We can test that just by multiplying that together with FOIL, with the first outer inner last. So the first would be x squared, the outer would be minus x, the inner would be plus x, and then the last will be negative 1. These cancel, and you see we do get back the x squared minus 1. So we see that this first line is actually that. So now when we have this, we see that these two things cancel. So what that really is the limit of x as x approaches 1 of simply x plus 1. And now, since we have this in the simplest form, now we could just plug the number in, and we can say this is going to be 1 plus 1, which is 2. And it so happens that the slope of a line of a parabola, y equals x squared, at the point 1, 1, the slope at that point is 2, right? Another way you can do it is if you look at this chart on the left side here, you see what they did was that's what it was, they just picked smaller numbers than I did. And they picked the 2, and they didn't put what the value is. So x is 2, x squared would be 4. But as you can see, they still got 3 just like I got. They just didn't show the whole process right there. So when x is 2 and the other point is 1, 1, the slope at that point is 3 between those two lines. When you get closer to 1, the slope is 2.5 and so on and so forth. And when you get to 1, 1 for one point and 1.001 and then 1.001 squared for the next point, and you do this same plot process of manually finding the slope, you see that the slope is 2.001. And the same thing, we come from the other side from smaller numbers and get closer and closer to inputting 1, we see it approaches 2 on the other side. So basically, if we keep putting closer and closer numbers, but we make this number even closer to one, and it's 1.00000 infinite zeros, we'll get closer and closer to 2 point infinite zeros and then one. And then we'll find that the limit from both sides converged is at 2. So this is basically a roundabout way of doing what this process here did, which is simply finding the limit. So that's what limits are about. Now, the way this relates to derivatives, if we look at for instance, the rise over run, we showed that it was the change in y over the change in x, right? Well, if you have something like velocity, that's basically the change in position over the change in time. That's why it's always like meters per second or miles per hour. There's some kind of distance over time. So basically what we're saying is we have a graph and we have, let's say, x here and t here. We want to get the slope of that rise over run, for instance. So you can say the slope of this line will be the velocity because we have rise over run or a change in x over change in t. This is actually the reasoning, by the way, that we utilize to measure the speed of light. We simply got the different times that it took for light to travel a certain distance, and we plotted the distance. And then when we found where those points matched up in the middle, we just plotted those points and then did a curve fit to connect those points. And the resulting line from the curve fit was the speed of light by simply finding a limit or getting the slope. All of these things refer, in a sense, to the same thing. So let me know if any questions come up from anybody who's watching. Um, But see what this thing is saying something is wrong with the keyframe, but as long as y'all are seeing it okay, I guess we're good. Maybe it's just responding to the new setup. It's awesome, good. Glad no questions. So I have a little bit of limits, a little bit of derivatives. We'll talk a little bit about some differential equations, which I had mentioned I was going to have a talk and go in more detail about this. Uh, but this will just be touching upon it a little bit, and maybe I'll talk a little bit about the problem that we were working on. So basically, we actually pull that problem up. We could take a look at and see how these differential equations work in operate in real life. So, boom, there we go. So we were working on might need to look up the problem, but I remember the problem anyway because I had to go over it so many times. So the idea is that we have, so we're looking at the atmosphere, and we're considering a certain patch of atmosphere. Like let's say this patch here that we'll call DZ. And if you pick any point in the atmosphere, this point or this slab of air, it will have a certain mass. So there's a certain mass of air, and this mass will be carried by this slab of air below it. And another thing that'll be affecting it is the pressure from the air above. So this mass of air here will be weighing down on that. The pressure from up here will be also pushing down on that mass, which is increasing the force that's pushing upon this lower mass. And at the same time, this lower piece of air will be pushing up to keep it from falling down and falling through. And basically, what we had to do was calculate or derive an equation to determine the change in pressure compared to the height above the surface of the Earth. And we had to derive that equation. But through a long number of processes, for instance, recognizing that pressure can be described as force times area. So you have a force distributed over an area. And I'm kind of forgetting whether it's force divided by area or force times. I have to think about that. There's one of the two. So basically, pressure, even though, like, if you have a what we consider to be pressure, something bouncing off this and pushing on it, the acceleration we can measure the pressure of. But the actual pressure itself is just force divided over an area. That's true. But the way it works is this slab of air is pushing on this slab of air, so there is a force there. So we have to count that as pressure because it is pressure. It's a force divide going by area, but then don't quote me. I don't remember it's F divided by F times, so one of the two. So basically, we can call this, for instance, the pressure uh, times an area going down. Oh, hold up. That's what it is. This force is the pressure times the area. So they come back to me. So we can call this, let's say, P prime A, that force going down. We can say that this is mg because again, this mass is resting atop this area. So this slab of air is filling that mass, just like how my hand is filling this pencil when I lift it, right? The mass is I'm holding this pencil up, but there is air pressure pushing on this pencil, which I'm feeling, but I'm not necessarily lifting the air. I'm lifting the pencil. And we can say that there's some pressure here that's also pushing up. So now we end up having uh, two forces of pressure pushing down and one going up. And the reason why this slab of air is not going anywhere is because all of these forces equate to zero. So this is a common thing you run into in classical dynamics, and that if you have, like, for instance, the common Newton's law, if you have a body in motion and you don't affect that body, it's going to just keep going in motion forever, right? So basically, at that point, you have a body moving in free space. The net force on that body is zero. So we have, as we have in real life, layers of pressures of air. The net force on that pressure of air, and there's wind and things like that in real life, but generally, at least for approximations that we're doing here, you can consider that certain pressure of air in the middle, the force on it equates to zero. So we can say F net equals zero, which is going to be negative P prime A um, minus mg and plus PA, and all that's going to equal zero. So there's a complicated process of breaking these things down, which I don't think is really worth doing because it just takes a whole lot of time. All that to get to what I was talking about, which is we end up with dp over dz equals negative rho v. Remember, right, that's g. Yes, because the mass is contained in the uh, um, uh, density here. So this ends up being the density of the air in the middle here. This ends up being gravity pulling down, and the pressure will change in relation to the density of the air and gravity. So a lot is included in this term because the density of the air will change by height. So in a sense, we could think of the change in pressure because of height, or you could think of the change in the density of the air because of height, which results in a change in pressure because the air is less dense. So all that is included in this density term, and now we end up getting closer to a differential equation. But what ended up happening is we needed to put this in a different term because the so this is a differential equation, right? But is an unsolvable differential equation because we don't know what the pressure is. So this is basically the derivative of the pressure as it changes according to height. We don't know what that is. And this is a density that changes according to height. We don't know what that is. So basically a differential equation, you have to have one, or generally one equation that you're solving for on both sides. And that's what we're looking for. So what we could end up doing is, and it might be worth pulling this up. But what we end up doing is taking this density here and putting it in the form that is also a pressure. By for instance, recognizing that uh, density is going to be a certain amount of mass over a certain amount of volume, for instance. But recognizing that we have equations that include those terms like PV equals nRT or PV equals kRT. So nRT is the number density, excuse me, the number of moles of a particle. So for instance, if you have this many moles and you multiply it by Avogadro's number, then you get how many particles you have. Um, and this one basically is a more complicated way of writing that by taking into account Boltzmann constant. So suffice it to say, it's a long process going through all of this stuff. What I had to do was took me 2 days to get it. Because the first day I talked to my professor and he explained part of it, and I worked on it. And went back the next day to office hours and I worked on it a bit more. It's long and complicated. Maybe what I'll do is do the whole thing next week after I had another chance to look at it. So as I say, it's complicated. And I don't even think I could explain it well. I went into detail right now. But I'm just going through this to give you some background of how we get to this differential equation. It ends up being complicated. But trust me, differential equations everywhere. You go through a whole bunch of stuff, and what we end up getting is dp over dz equals negative p, and what do we have here? I think we still had g here. We still have some kind of constant there. And what ends up happening is now we end up with a differential equation. And actually, this was a whole lot more complicated. I think I actually made it a simple constant to, because what I was realizing was it was something like uh, the k constant r over v mass. It was just something crazy, and then times p. And I was trying to figure out how to do the differential equation, and my professor was like, "No, it's just a regular differential equation. You solve it the same exact way." And I was like, "Well, let me think if I can put it in a form that I'm familiar with from differential equations." So remember that this is the change in pressure given a certain height, and this is just the pressure times a whole bunch of constants and masses and stuff like that. That's basically a derivation that comes from this density. Like there's a whole bunch of things we have to go through. Let me know if you're interested. I said, sure, but paid. Yeah. And you can understand why people who pretend to know science do that because this stuff is hard. Going through the details is hard. But it actually gets fun when you start to understand it. Like, like one thing that's surprising me, and I'm gonna have to, like I said, and when I get through this perturbation thing a bit more, I'm gonna spend a day talking about that. And one interesting thing, now I told you all the problems I had with quantum, right? So quantum one, I didn't do so hot. I would have gotten a C, but I just made it pass fail, and I took it again. And the second time, this is my second time going through the whole course, I got a B minus. So it's not my forte, right? But now that I'm taking quantum two, everything you did in quantum one, they just assume you know. And I'm finding that actually a lot, right? Like we're solving for perturbations and it's built upon what we know. And I found that I'm able to go through the original stuff pretty well. So the stuff, as you work with it, it does start to stick, but it does take a lot of work. Now back to the differential equation, the pain. And even says, oh yeah, when first pretend to know this stuff and lie about it, so frustrating. I find it's frustrating when you care. Like it was frustrating when I was talking to the liar glow denier the other week, the self-admitted liar glow denier. But after that talk, I realized it's just no because it all crescendo like with the final experiment and trying to actually just have just a not a debate, but just a conversation with this guy and just see how they respond with the lies and avoidance and just trying to just a bunch of games. I realize just I don't care, it's just pointless. I think at some point I thought maybe you could reach some of these people, but you can't. But it takes so much, it's just not worth the time. Like I was saying the other week, who's gonna spend like $30,000 to send all of them to Antarctica, right? So it's definitely easier just to pretend like you know and don't do the work, right? This stuff is hard. But you can take this equation here and you can just do like this. You can just say, or a matter of fact, let's go x dot equals, let's say ax. Now, if you look at this, this is actually the same equation, but this is just the form that I'm so used to seeing equations in. So if you look at this dt dz, this is basically the space derivative of pressure. So this is basically, you can say p time, and this is basically the time derivative of position, or you can say dx over dt. But even though they're talking about different things, this one is talking about pressure versus position right here. This one is talking about position versus time. Still, there's something changing relative to something. And think back what we did about the limits, right? We talked about the change in y over change in x. So the limit, right, that ended up being a derivative like a velocity. These all relate. But this is just a form that I'm used to seeing it in, right? And this is just pressure, just like this is just position. And this is just, it ends up being just a constant. When you multiply everything together, it's just a constant or a number. And this may actually makes more sense. Now we're getting to just a regular differential equation, which is x dot equals ax. And this is what's called, it should be an ordinary differential equation, right? Because we look at it, it's just a derivative of something on one side and something times the function that's being taken the derivative of on the other side. So this is the derivative. The x dot is a shorthand for derivative with respect to time, and this is just x, whatever x is. And as my professor reminded me the other day, when you get a simple ordinary differential equation, the proper way to solve it is to guess. And there's actually a few ways to solve this thing. So, but the simplest way is just to remember that if you have an exponential, let's say ex to the a, whenever you have an exponential and you take a derivative of it, it's always going to be the exponential again times the derivative of whatever in the exponent. So if I take the derivative, let's say of x of this, it'll give me whatever the exponential was again, plus the derivative of whatever was at the top. So that's going to be this again, and the derivative with respect to x of xa, it is going to be a. So what I end up with is ex or alpha and whatever x was initially, because I guessed that this would be my x. You see that? So right there, we actually solved the differential equation and said x or dx dt equals ax. We'll say that x of t is e alpha x, and another uh, detail, in terms of writing it as alpha and otherwise, that I missed on the problem is that, hold on. So this will come down when we take the derivative. So basically this is x. The derivative of that will be x times a. And if this is x, the derivative does end up being ax. So it does match up. Now, the thing about this a right here, this a is actually all of this crazy stuff here. So all of this crazy stuff here in the real problem ends up being what we just called a. And then what I was able to do is just, go back to the equation and just rewrite it in the proper form and say p of z equals e to the negative, all of that crazy stuff, and then z, and then that ended up being a solution to the equation, right? So it's pretty much a simple way to solve differential equations and looking at the going from limits and noticing that they're derivatives. And then now we have basically equations that are made of derivatives and finding a function that fits into those equations. So this is actually a good review for me because I was getting stuck on these things trying to solve the more complicated problems because I didn't do these things anymore. Any questions came up, Lisa, or anybody else? Before I move to the last topic, some cosmology, and we'll tie this a little bit into Hubble's constant, which we've been studying a lot in our cosmology class. And thanks to those who are watching. Be sure to drop a line, like, subscribe if you haven't. And if you have any questions, let me know. Also, so Lisa says she's cool. So cosmology. Now this book, I don't have it in uh, uh, digital form. I just have it in paper form. I won't be able to share the actual book, but I'll be able to write out what I'm talking about. Are you familiar with the Hubble constant, Lisa? What that's about? Like, how familiar are you with the whole Hubble constant? That'll let me know where to jump into the topic at. Jump into like a full explanation or jump into the math of it. Okay, let's talk. Let's start with the beginning. So the idea is, the ironic thing, by the way, Hubble was right and wrong. So, all right, there was this lady. Her name was, should know it. It was Cecilia Payne. Was it Cecilia Payne? Or hopefully I'm not mixing up which ones it was. But let's just say it was Cecilia Payne right now. It might be somebody else. Let's say it's Cecilia Payne. And what she discovered was that there are certain stars in the universe that have a period. And somebody who's watching, if it's not Cecilia Payne, let me know if it's somebody else, but I think it's Cecilia Payne. But she was studying stars and realizing that there were certain stars that that rolled at a regular pace. And there were stars like that that's close enough in the Milky Way galaxy that we were able to get their luminosity. And what she learned was that these certain stars, these periodic stars, they had a certain brightness that was tied to their luminosity. At least their luminosity was tied to their period. So if you had a certain period, you had a certain luminosity. And it became so consistent that it became a certain scale that if we have a star that takes this long to strobe, is this bright. If it takes this long to strobe, is this bright and this bright. So we had basically a distance scale just from looking at stars. What Hubble did was he took that and we started looking at distant galaxies and finding these strobing stars. And what he found was when he looked at a distant galaxy and he found the strobing star in that galaxy, and he was able to say, okay, it's strobing at this pace, so we know it's this bright. We're able to take that luminosity and find out the distance from us to the star from the flux. So basically, we can say the flux is the luminosity divided by the area that the light is expanding upon. The aura is going to be the distance to the star. So we know how bright it is from looking at it. We can go ahead and solve for R. So basically we can say we know the brightness from the strobe. We know how bright it is from simply looking at it. And then we can say that R squared equals L over 4 pi L. And R equals square root of L over 4 pi. What's R? Or F. That's what I did. So this is actually F. There we go. Boom. So now we can get the distance to anything, any star that we can get the luminosity from looking at the period. And if I see that equation up in here, I'll check and make sure I didn't mix up one of the letters, but pretty sure that's what it is. But I'll run into it in a bit, or I'll just talk about it, come back to next week. But this is the concept or the idea behind it. We know how bright these stars are by how much they strobe. We can look at them and see how bright they are, and thus we can look at how bright they seem to be versus how bright we know they are, and we can get the distance from us. But when Hubble did this, what he found was that the stars that are farther away, they seem to be moving away from us. And we're able to see that from the redshift. We're basically looking at a star in a galaxy, and we know that the brightness should be this and the color should be this. We're noticing, hold up, it's redder than it should be. It's moving away, just like how when a car moves away from us with a siren blaring, these siren sounds, coming towards us, it's like, yeah. Then when it goes away, it's like, yeah, because it's slowing down because of redshift. Another thing he found was that the farther a galaxy is away from us, the faster it's moving away from us. And he basically measured this and said he looked at a whole bunch of galaxies and found that there's a linear relationship between how far the galaxy is away from us and how far it's moving away from us. And this slope is what's called the Hubble constant. This constant that says if a galaxy is this far away from us, is moving this much faster away. That's correct, the Doppler. But it's Doppler with light. So the current value for the Hubble constant is about 70. And let me actually look at this one to make sure I get the units right. The Hubble constant is, well, the official one right now is 68, and it's kilometers over seconds milliparsecs. So basically, for every milliparsec, the way you look into the universe, a galaxy is going 68 kilometers per second faster away from us. And this ends up giving us many cool equations, like a few we had to use to solve for some problems recently, as far as the distance of things and finding out where things are, the redshift of things. We found that the redshift of something, as you call the Doppler shift of it, which we call Z in astronomy, is equal to the Hubble constant divided by the speed of light times R. R being the distance from us is the same R that I wrote here, but sometimes they write it in uppercase, sometimes they write it in lowercase. I'll just keep the same uppercase notation. We could also say that the velocity of something moving away from us is going to be the Hubble constant times its distance, right? Because again, every single milliparsec away from us is going that much faster away from us. So let's say we have a galaxy that's 100 megaparsecs away from us. We can look at the galaxy, how bright that strobing star in it is. We know how bright that star is because we was able to see so many stars strobing that bright, and every single one of them is this bright, except for a little bit of a difference, but they're pretty much right in the middle, this bright, so we can get the distance to that thing, right? And when we plug that in, we can say HO times distance, or HO times R, which would be, and I'll just round it to 70 kilometers per second per megaparsec times 100 megaparsec, right? So the megaparsecs cancel. And what we find is when we look at that galaxy, it's going, what, 7,000 kilometers per second away from us. And we can tell that because we get the Doppler shift related to that. So basically, if we take this same thing and we put in the Hubble constant, we put in the speed of light times r, we'll find that we have a certain Doppler shift related to this velocity, and it all adds up. And what you could also do is put these equations together, and let's see, so I have this equation, they both have h in them. So if I solve for h, I can see that H naught equals what ZC over R on that side, and H naught equals V over R on this side, right? Keep trying to keep the capital letter notation. So now these two things equal each other. I can cancel out the R's. So now I can see that the velocity is going to be the speed of light times the redshift away from us. So we could also get the velocity of a galaxy away from us by looking at the amount of redshift it has from simply studying the light up from it and seeing how much is redshifted. We multiply that by the speed of light, and the velocity we get is the same velocity we get from applying uh, the Hubble's derivation. So all of this stuff adds up, and this is the what do you call it? I forget the exact word. There's some cool sciencey word for it. Uh, Something with an R. But the galaxy was moving away from us. Sometimes we get a little fancy words to use. But that's cool, right? So you can see how velocity, redshift, the Hubble constant, the distance away from us, all of these things relate in a very mathematical way. Now, earlier I said that Hubble was right, but he was also wrong. And the reason why I said that is not in. Let me find it. I'm sure I'll be able to run into it soon enough. Recessional, not recessional. Mm-hmm. Relative. I hate when I can't find a certain word, and I know, and usually what happens is as soon as I start thinking about it later, like soon as like right after the stream ends, it'll pop in my mind. But I believe it's recessional, recessional velocity. It sounds pretty much right. Recessional velocity, the velocity that's moving away from us. Oh, that's a Monty Python ref. I saw that, but it's been a while ago. One of my favorite classes was I took a class at community college for one of my electives. It was a film studies class, and I like movies, and I wanted to get my degree. So a class where we had to watch movies for a grade, oh, that was awesome. So, I don't remember which one we saw, but I know we saw one of them. Apparently, there's more than one. That was a fun class. I enjoyed it. But awesome. That's pretty much what I had. Talking about a little bit of derivatives, a little bit of limits. Oh yeah, it was fun. So, matter of fact, the first video we watched, the very first assignment, was to watch "This Is America" by what is his name? Gambino, something Gambino. That's the first thing we had to watch. And the good thing about this professor, he wasn't like trying to push an agenda. Like we watched a multitude of different things. A lot of them were old. I guess I can say that several of the movies were old movies, but some of them were new as well. But he wasn't trying to push an agenda, and you didn't have to uh, try to regurgitate a certain thing like a lot of the gender ideology, critical race theory people do. Like pretty much, they want you to tell you what to think. We could pick whatever angle we wanted. We just had to just analyze it and find something, was a bit more focused than just anything. But we pretty much had free reign. It wasn't like he was trying to push any kind of agenda, so it was pretty cool. He says, I saw Casablanca for the first time in theater last Wednesday. Amazing movie, interesting. I never saw Casablanca. Was that in black and white? I of course heard of that movie, but I never actually seen it before. Maybe I need to. I've also been meaning to watch uh what is this movie? It's this movie, there's this robot in it. I know there's one called Chronos. There's a few old movies I've been meaning to see, but I never took the time to see. It's really good. Thanks. So most likely, I mean, I watch a little something, but usually while I'm watching something now, I'm like doing homework at the same time. Like I watched the whole Hunger Games series technically over the weekend, but the whole time I was coding because I've been working on my research. So, which I'll talk about to y'all in the future. I know I mentioned my rotation of math and perceptive research. Man, my coding got a whole lot better since taking that course. So I'll be able to talk about that soon too. Lisa says North about Northwest is my favorite old movie. Thanks for giving these titles. Probably when spring break comes, I'll probably be able to sit and actually watch an actual movie. Like I haven't really been able to just like watch something in a while. Usually I'm like coding or trying to do some kind of homework on the side or something. But it's just something like when I'm starting to get tired just to keep me going. But also, hopefully y'all enjoy it. So I don't know how the topics came across, but all of the topics that we went over today are things that I'm covering in class, particularly this week. A few of the things that gave me problems that I had to look into a bit more. So that was a good refresher for me, and hopefully that tipped y'all off a bit. And these are some of the foundational things that ends up adding up to big things. Like I showed that example of the problem where we're actually getting equations for calculating the change in pressure over height. And it isn't being an estimate, not 100% accurate, but it's pretty accurate, in the scheme of things. Like if you needed to decide, should I bring an oxygen tank with me? The equation that we gave you will give you a good estimate on the conservative side. Hey, I'm going to this high on the mountain to probably bring some oxygen, or maybe not. It's a good enough estimate, for instance, to you know decide if you want to bring it roughly. It sounds a better suggestion. Awesome. So I'll be back next week. Remember to drop a comment. Maybe I'll make another comment line of anything y'all want me to cover. But a few things came up just in this one, with more detail on derivatives, the long haul of that thermodynamics problem, perturbations and quantum two. So much stuff to talk about, but I guess it'll be which one I could explain the best by the time next week comes. So if y'all have a preference, let me know and I can focus on that one. But we'll start with one of those next week. So awesome. Thanks everybody who joined, for everybody who watched. Make sure to comment, like, subscribe if you haven't already. And I'll see y'all next week, if not before. You're welcome, Lisa. Always good seeing you. That'll be cool.